The question was if two carts, one of mass m and the other of mass 2m, are pushed on with the same net force for the same time, which cart has greater momentum? And we determined that since F net delta t is equal to delta p, and this is assuming a constant force, although it doesn't need to be a constant force because we could integrate it and find the same thing, that F net delta t equals delta p, and so since F net is the same for each cart and delta t is the same for each cart, then delta p is the same for each cart. Same for each cart. So notice what happens is that the smaller cart, since it's the change in momentum is the same for each cart, if each cart starts from rest, then one cart, the smaller cart, m and 2m, the smaller cart is going to go farther in that, faster in that amount of time, and therefore also farther. It's going to have to go faster because it's smaller, and if it's got the same change in momentum, if the change in momentum for the small cart is the same as the change in momentum for the big cart, remember the change in momentum is going to be mv final minus mv initial, or m change in velocity. So since it's got a smaller, let's do the other one, 2m delta v, since it's got a smaller, because they've got different change in velocities, because they have different masses, and the momentums are the same, or the change in momentum is the same, therefore the final momentum is the same, because they both start with a momentum of 0, then the smaller cart must be actually going twice as fast as the bigger cart. But in any case, the answer to the question was same for each cart. So the next question I have, and I've given away some of it here, some of the answers to the next question, is which cart has a greater kinetic energy? So I've written that down. Which cart has a greater kinetic energy? Think about it. Answer coming in 3, 2, 1. Okay, so the answer is the smaller cart has the greater kinetic energy. Smaller cart, or the one that has m, has greater kinetic energy. Do you see why? There's a different way. There are a couple of ways to see it. One is that the smaller cart, right, the velocity of the smaller cart must be twice the velocity of the bigger cart, because the mass of the smaller cart is twice the mass of the bigger cart, and the momenta are the same. So this speed is twice this speed. Kinetic energy, let's write it in the corner, ke equals 1/2 mv squared. Since velocity is squared, then since the velocity is doubled but the mass is halved, then the velocity term wins and the kinetic energy of the small cart is bigger. Think about that. We're using proportionalities. You can think about that. But the other way to see it is the change in kinetic energy is the total work done, right? The total work done is the change in kinetic energy. The total work done, remember, is the net force times the displacement equals the change in kinetic energy. So just like for the other, for part A, we had that the impulse, F delta t, is equal to delta p, and we knew that F is the same and delta t is the same, so delta p was the same. Well, in this case, we can look at F net times d and see if delta k is the same. So the net force is the same, but what about the distance? Which one goes farther? And you had to think about that, but the small one goes farther, right? The small one goes farther because it's easier to move. Small one goes farther, it's easier to move. So it's going faster, and so it must be going farther. And so F net d is bigger. F net d is bigger. So the small cart, since F net d is bigger for the small cart, it has more kinetic energy. Okay.